Hello everyone. Today we're going to talk about electron configuration, essentially a map to where an electron is located in an atom. So normally when I get to teach electron configuration, I actually change the classroom so it looks like this. However, since we can't do that, we're in cyberspace, we're going to essentially use a periodic table very similar to this, but in a digital form. If you notice on this periodic table, I've divided up everything into 4 distinct sections. So all the way on the left side, we have what's called the S block. In the middle here, we have the D block. On the right side, we have the P block. And all the way at the bottom here, we have the F block. Now, we're not going to talk very much about the F block, but I wanted to make you aware of it. This is just a reminder about the shape of the different orbitals that we're going to talk about today. So the first one is the s orbital. The s orbital is spherically shaped, or shaped like a sphere. So if you imagine the first energy level, 1, out in front, s orbital looks like a really small sphere. When you go and add on the second energy level, that's like a bigger sphere that covers or encapsulates the entire first energy level. And the third energy level sphere is bigger than that. The p orbital is not a sphere, so the p orbital is shaped like a dumbbell. And you'll notice that it has 3 different possible orientations. So along the x-axis, along the y-axis, or along the z-axis. The d orbital has 5 different possibilities. So if you notice, there are more complex shapes as we keep going. So the d orbital looks like it has 2 areas of electron density, and that could be centered around the x and y, the x and z, or the z and y plane, depending on which one you're looking at. And then there's also 2 additional orientations. When we take a look at the F block orientations, you can see how much the complexity has increased. So if you look at the shapes of these orbital clouds, they're much different than what we saw when we looked at the S and the P orbitals, which were very simplistic. So the good news is we're not going to worry or focus too much on the F block, but if you imagine superimposing all of these different cloud shapes on a single center, you get what looks like a giant mess, or better, what we call the electron cloud. So now we're ready to start looking at the electron configurations for individual elements. One of the things that I would like to point out is that much like your home address, the address for a specific atom and a specific electron being added is very similar. So you, when you write your address on an envelope, probably start with your name, then you list your house and street number, and then the town in which you live in. We're going to do it in a very similar, but also exactly opposite direction. So we're going to start wide and then kind of narrow into where that particular atom is located. So the very first part of our address is going to be the energy level. And the energy levels can be found right here along the side. So we have first energy level, second energy level, third energy level, 4th, 5th, 6th, 7th. And then I'll explain these are really 4 and 5 because they fit up in the table. But we don't have to worry about F block. The second part of the address is what color block you are in. So the second part of the address will either be S, P, D, or F. So depending on where that atom is located in the periodic table, we will use that corresponding designation up here, S, P, D, or F. The last part of the address is like the house number in your address. So the house number is going to be based on these numbers that are at the top of the column. So we have house number 1, we have house number 2. Here we have 10 different houses, and here we have 6 different houses. So 1, 2, 3, 4, 5. And that 6 corresponds to everything that's over here. This 2 that's up here only is associated with helium. So putting this all together, the address for our first element on the periodic table, which is hydrogen, will be energy level 1. It is in the green block, so we're going to put an S here. and it is in house number 1. So 1s, and then the house number, which actually corresponds to the number of electrons, is a superscript 1. Our second element, which is helium, will have a similar address. It is also located in the first energy level. It is also located in the green space over here, so it's also an S. And we mentioned earlier that it's located underneath this 2, so we're going to put a 2 as a superscript. One thing that I want to point out is that the superscripts should match the number of electrons that an atom has. So hydrogen has 1 electron because it has 1 proton, so it has 1 electron here. So 1 electron total. Helium has 2 electrons total. Now let's look at the street address for lithium. So lithium is now in our second energy level. So in our second energy level, we're going to start off with a 2. And we're still in the S block. So we're going to write that S down. And we're at house number 1, so we're going to write that part down. You may notice we have a problem. And the problem is that right now, the superscript doesn't match the number of electrons that we find in lithium, which is 3. So in order to fix that, what we're going to do is we are going to include the 2 electrons in the 1s sublevel. Now, I've been using this example of a house location, but what we're really doing is building levels, energy levels in an atom. So if you think about a Bohr diagram, so a Bohr diagram would look like this, energy levels that radiate out from the center. Lithium has 2 electrons in the first energy level, and then 1 electron in the second. So 2 electrons here, 1 electron here. These 2 electrons are in the first energy level. This 1 electron is in the second energy level. A good way to think about this is that anytime you complete an energy level, so you move from first to second or second to third, all the way on the right side, or anytime that you complete a sublevel, so you go from S to P or from S to D, you're going to write down that number, and that number will become part of every element that comes afterward. So those special spots are going to be anytime you cross over here, all the way down, anytime you cross over here, all the way down, and anytime you cross over here, again, all the way down. So if you cross any of those thresholds, the last element before you go across becomes part of every element afterward. So let's take a look at beryllium. So we're going to start here. We're going to go all the way across. We hit this pink arrow. We're going to write down 1s2. Now, we start on the second column, or second row, excuse me. We move to the second column, and we stop at beryllium. So we're going to write down energy level 2, S, because it's green, house number 2. So 2s2. Let's take a look at boron. Again, we're going to start here. It's like typing on a word processor. You go all the way across, then you hit enter and go down to the next level. So we're going to go all the way across. When we hit this pink arrow here, we're going to write 1s2. Now we're going to start on the second energy level. We're going to go across. We hit another pink arrow. So we're going to write this down. So that becomes 2s2. Now we keep going because we're trying to get to boron. So we're going to go all the way across. And we're going to stop right here at boron. And at boron, we're going to write down second energy level, P block, because now we're in the orange space, house number 1. So 2p1. Let's go back and check some of our work. So for lithium, notice we have 2 plus 1, or 3 electrons total. For beryllium, we have 2 plus 2, or 4 electrons total. And now for boron, we have 2 plus 2 plus 1. We have 5 electrons total. I'm going to try one more, then we're going to skip around a bit. So let's look at carbon. Carbon is element number 6. So again, we're going to start at the top here where hydrogen is. We don't have to write anything down, no pink arrow here. So we're going to keep going. We get to helium, we write down 1s2. Next, we start on the second energy level. We go across, we hit our first pink arrow here. So we're going to write down the address for this, and that is 2s2. Next, we keep going. We don't hit any pink arrows. We finally land on carbon. So we're going to write down second energy level. So 2p, because we're in the orange spot, and 2. 2p2. And here we have 2, 4, 6 electrons total. Which is perfect because carbon is 6. So now we're going to jump ahead a little bit. So let's take a look at neon. So neon is all the way at the end here. I'm going to go ahead and add my pink arrows back in. So they're going to go here. Anytime we cross that. Anytime we cross here. Anytime we cross here. So if I'm going all the way to neon, start up here, I get to my first pink arrow, I write down 1s2. I'm just going to erase the top here so we don't get confused. There we go. I go across the second energy level. I hit this spot. I write down 2s2. Now, I'm going to go all the way to neon, which happens to also be where my next pink arrow is, and I'm going to write down 2p, because we're in the second energy level, orange block, spot number 6. So 2p6, for a total of 10 electrons. Now let's take a look at sodium. So if we notice, sodium is right here. Sodium is going to start off, we're going to start up here, we're going to go across to helium, we're going to write down 1s2. It's our first energy level complete. Now we're going to start on the second energy level. We get to the first stopping point right here. We're going to write down 2s2. Now we can keep going. We go all the way across the second energy level. We stop at neon, because that's where our next pink arrow is, and we're going to write down 2p6. Now we're done with the second energy level. We're in the third energy level. We're going to stop right here. So we're going to write down 3, because we're in the third energy level, S, and then spot number 1. So 3s1, total of 11 electrons. Let's try another one. Let's look at magnesium. Magnesium, we're going to start all the way at the top. We're going to go all the way across. When we get to helium, we write down 1s2. Now we start on the second energy level. We hit our first stopping point. We're going to write down 2s2. We keep going all the way across. We hit our next stopping point. We're going to write down 2p6 because we've completed now the second energy level. Now we're in the third energy level. We don't hit anything here, so we're going to stop right on magnesium, and we're going to write down 3s2. So I have 2, 4, 10, 12 electrons total. Okay, we're going to skip a little bit. So we're going to go all the way this time to Si. So we're going to start at the top here. We don't write anything down. Bam. Now we stop at helium. We write down 1s2. Now we start on the second energy level. Oh, we hit our first stop point right here at beryllium. We write down 2s2. Now we keep going all the way across. Our next stopping point right here at neon, we write down 2p6. Now we're into the third energy level. We go across, we hit our first stop point right here at magnesium. So we're going to write down 3s2. Now we're going to keep going across, and this time we're going to stop right on Si. So there's no stopping point here, so we don't have to write anything down for Al. We're going to stop right on Si, and we're going to write down 3p2. Notice 2, 4, 10, 12, 14 electrons, and Si is element number 14. Okay, let's skip all the way to argon, which is all the way at the end of that energy level. So again, we're going to start at the top. We're going to go all the way across. We're going to stop at helium. We're going to write down 1s2. Next time, we're in the second energy level now. We're going to go across our first stopping point right here, 2s2. Now we're going to go all the way across, and our last stop in the second energy level is right here at neon, so that's 2p6. Next one, third energy level. I go across, I hit my first stop here at magnesium. Sorry about that. So that's 3s2. Then I keep going all the way across. This time I'm not stopping until I get all the way to argon. So argon, I'm going to write down 3p6, and I have a total of 18 electrons. And then finally, my last one that I'm going to try on this page is calcium. So we're going to go all the way across. We're going to stop here. We're going to write down 1s2. Start here on the second energy level. Go to our first stopping point. We write down 2s2. Next part, we're going to go all the way across, and we're going to stop right here. We're going to write down 2p6. We're going to start in the third energy level. Here's our first stopping point, 3s2. And then if we continue all the way across to argon, we're going to stop at argon because that's our next stopping point. We're going to write down 3p6. Last one. We start on the fourth energy level. We get to calcium. We're going to stop there, and we're going to write down 4s2. So fourth energy level, S block, spot number 2. By now, you might feel pretty comfortable with what's going on. And that's usually the perfect time for chemistry to throw you a curveball. And that's what's going to happen here. When we start to talk about elements in the D block, there's one thing that we need to be aware of. And that one thing is that the D block elements are actually placed in a lower energy level. So when we are in the fourth energy level, we have 4s1, 4s2. But once we cross into the D block, we actually are moving into the third energy level D block, the fourth and the fifth. This only applies to this blue section here. So this only applies to this blue section here. So when you are in the fourth energy level and you go and transfer into the blue spaces, you're actually going to start off with a 3, 4 or 5, depending on where we are. So let's take a look at our first example, which is scandium. So as I move across, this part doesn't change. I stop when I get to helium. I write down 1s2. Then I pick up second energy level. I stop at beryllium, just like I did before. I write down 2s2. Keep going all the way across. The next stopping point is over here at neon. I write down 2p6. Start on the third energy level. First stopping point is right here. I write down 3s2. Next, I continue all the way across. I stop here. Again, I write down 3p6. Start on the fourth energy level. Here's my first stop point, 4s2. And now we cross into that blue section where it trails by 1. So this spot here, even though it looks like it would be 4d1, is actually 3d1. Now, what happens here is that the third energy level, D sublevel, is really close in energy, but slightly higher than parts of the 4s sublevel, which end up filling in electrons before. So the best way that I can explain this is if I draw the sphere for the 4s sublevel, and then I draw over the top of it the clover leaf for the 3d sublevel, you'll see that the sphere is actually slightly lower in energy than parts of that clover leaf. So what ends up happening is 2 electrons will slide into the 4s sublevel, and then electrons start getting added to the 3d sublevel. Again, they're very close in energy, but 4s is slightly lower in energy. All right, trying our next example, which is vanadium. We have 1s2, that gets us to helium. 2s2 gets us to beryllium. 2p6 gets us to neon. 3s2 gets us to magnesium. 3p6 gets us all the way across to argon. 4s2 gets us to calcium. And now we're going to vanadium, which is right here. So we're going to end with 3d3. Now, if I jump ahead and I look at iron, iron is going to look just like vanadium does. The only difference is instead of ending at 3d3, iron will end at 3d6. So I can copy down all of this, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then I could just change the 3 on the end to a 6. If I look at nickel, it's going to be similar, but the ending will be changed to an 8. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. And then finally, if I go all the way to zinc, the 3D will change from an 8 that we had in nickel to a 10. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and finally 3d10. Now, just to prove to you that the number of electrons is still equal to the sum of all of those superscripts, let's take a look. Here we have 2 plus 2 is 4, 10, 12, 18, 20, and then 10 more adds up to be 30. So zinc has, as we would expect, 30 electrons total. Like most things in life, there are a few exceptions to the rules when it comes to writing electron configurations in sodium. So this next portion of the lesson is specifically tailored toward accelerated honor students who will need to know these 4 exceptions to the rule. So before we start talking about the exceptions specifically, let's talk about why they occur. So basically what we start to see is different levels of stability depending on the electron configuration. So at the top, the most stable electron configurations are when you have full energy levels. This is when your electron configuration ends with a P6. Any of your noble gases will have this. Neon, argon, krypton, xenon, any of those are going to end as P6, and they're extremely stable. The next, most stable, would be a full sublevel. So this would be an S2, a D10, something like that. Third most stable would be a half-filled sublevel. So this would be an S1 or a D5. And the least stable would be something that is partially filled. There are a whole bunch of examples that I could include for this. So a partially filled would be something like a D3 or a P2. These are the least stable. So in terms of stability, the closer you are to the top, the better you are. So let's take a look at these 4 examples. When we write out the electron configuration for these 4 examples, I'm going to start by showing you what the electron configuration would be, and then I'll show you how it's changed as a result of these exceptions. So for chromium, based on what we currently know, we would have an electron configuration that ends as 4s2 3d4. We talked about this earlier. The S sublevel and the D sublevel are very close in energy to each other. So what ends up happening is when you have a situation like this, an electron can be promoted from the S sublevel to the D sublevel. The advantage and why this occurs is because we take a 3d4, which would be a partially filled sublevel, and we turn it into a D5, which is now a half-filled sublevel. The D sublevel can hold 10 electrons, so 5 electrons would be half-filled. This is more stable than this, and that's why this exception to the rule occurs. With copper, we have something similar. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. That 3d9 gets changed it becomes 4s1, 3d10, and now we take a partially filled d9 and we convert it to a full d10. So this, again, is more stable than this. Full sublevel is more stable than a partially filled sublevel. Just want to indicate that these are not connected. They're separate possibilities. Okay, the same thing that occurs with chromium and copper occur with molybdenum and silver. And they are directly on top of each other on the periodic table. Chromium is over molybdenum, copper is directly over silver. So in this case, for molybdenum, we would get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. This would now be 4d4, but that will change. This will become 5s1. This will be 4d5, again, going from a partially filled sublevel to a half-filled sublevel. And with silver, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. That's what we would expect it to be, but instead it becomes 5s1 and 4d10. There are more exceptions than this. We are only going to be responsible for learning these 4. Finally, for those of you who are overwhelmed at the thought of writing electron configurations for elements way down here like cesium and barium, there are some shortcuts that we can take. Now, we are going to learn both the full version, which I've talked about already, and this shortcut version. On the homework assignment that we're going to complete, we are going to have half of them where we will complete the full version, and the other half we'll be able to use this noble gas configuration shortcut. The noble gas configuration shortcut basically allows us to jump to the nearest previously completed noble gas, and then begin writing the electron configuration as we normally would from there. It's like a jump ahead. For the first 2 elements on the periodic table, since we have not completed a noble gas yet, their electron configuration will look exactly the same. When we get to the element lithium, we have now completed the noble gas helium. We've filled it up with 2 electrons. So we're going to be able to do, when we're looking at lithium or any of the elements in period 2 on the table, second energy level, we'll be able to jump ahead to helium. So we'll put that right there. And then continue on from where that is. So to indicate that we've jumped ahead to helium, we write the symbol for helium inside of square brackets, and then we continue as normal. So lithium, we would write 2s1. When we look at beryllium, we have the same element that was completed, helium. So when we look at beryllium, it's going to look very similar to lithium, but instead it will end as 2s2. Boron. So if we look at boron, the last completed noble gas is still helium. Then we will pick up and write 2s2, 2p1. And similarly for carbon, we're going to write helium, then 2s2, 2p2. Let's take a look at some additional examples. The next example that we're going to look at is neon. And everyone is tempted to say, perfect, neon is a noble gas. I'll jump right to neon. Well, it's the last completed noble gas. So if I'm standing on neon, the last completed noble gas is still back here at helium. So for neon, I would write helium, and then 2s2, 2p6. However, once I get past neon and I move to sodium, which is element number 11, now I can jump ahead to neon and work from there. So for sodium, I'm going to put neon in the square brackets and continue with 3s1. For magnesium, I would do the same, and it would be 3s2. For Si, I would do the same, and it would be 3s2, 3p2. And then finally, when I jump to argon, or when I'm going to argon, I can jump to neon and then write 3s2, 3p6. In our last example on this page, we look at calcium. So calcium is over here. It's element number 20. That means the last completed noble gas is now argon. So I can move this down to Argon and jump to Argon and continue from there. Now, to show you how much time this can save you, I'm going to do one more set, and I'm going to show you both the full form and how the noble gas shortcut saves us. So the first thing that I'm going to do is write out the full electron configuration for barium. So this is the full electron configuration for barium. And just to prove it to you, let's add up the electrons. 2 plus 2 is 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56. And barium is element number 56. What the noble gas configuration shortcut allows us to do is to jump to the nearest completed, previously completed noble gas. So if I'm at barium, which is element 56, the last completed noble gas is xenon, which is element 54. So my noble gas configuration for barium would simply be xenon in the square brackets, followed by 6s2. Okay, that completes our lesson on electron configuration. Please try both parts of the homework. Numbers 1 through 12, you will be writing out full electron configurations. Numbers 13 to 24, you will be using the noble gas shortcut, which will save you a lot of time and energy. If you have any questions, please consider stopping by for office hours this week. If you're looking for the specific time for office hours, that can be found on Schoology. Thank you very much, and I hope everyone has a great week.